Hello, welcome back to part 2 of Introduction to Physics. I couldn't quite fit it all in one lesson, so we have to break it up into 2 pieces. But my singular goal remains the same as we had in the lesson. My singular goal is just to get you excited about learning physics. We're not going very deep, we're going very broad. And by going broad, you can kind of see the lay of the land and see what the whole point of this is anyway. So in the last lesson, we started out talking about motion of objects and calculating their trajectories. We talked about work. We talked about kinetic energy, the energy of motion, potential energy, which is the potential to do some sort of work, right? And we talked about heat a little bit, and the motion of the atoms is what we know now to be the temperature of an object. And we talked a little bit about the idea of a wave. And the wave concept is going to be of incredible importance going forward because, as I mentioned in the last lesson, all of the modern theories of physics about how light propagates, how matter actually behaves, the electrons and the protons, they're all wave theories. And I know that that sounds crazy because we're never taught that like electrons and protons are waves. But in reality, when we get past all of this kind of like essential physics we need to get into and start to get into modern physics called quantum mechanics, they're all wave theories. Everything boils down to be a wave. So, or at least that's our current theory. So when we study waves in physics, it's important because we're going to carry that forward into the most current theories that we have. So we left it off in the last lesson. We talked about waves. And the roadmap in this lesson, we're going to go waves, we're going to talk about thermodynamics a little bit, and then we're going to talk about electricity and magnetism and Maxwell's equations, which, as I mentioned before, in my opinion, are the most beautiful equations, or one of the most beautiful sets of equations we really have. They describe how electricity and magnetism work and how waves of light waves come about from that. So we left off in the last lesson by talking about waves. This is a wave on a stretched string. So when you cause a disturbance, we see a wave propagate with some velocity v. We can cause another wave to go the other way with some velocity v, and these waves can collide and they can interact. Basically, we add these waves together. Now, if the crests line up together and the troughs line up together, then we end up with a bigger wave, and this is called a constructive interference because they're adding together and making the wave bigger, basically. All right? But we could have a situation where 2 waves come together, and notice that I've drawn this one inverted so that this trough is going to hit this crest, and this trough will hit this crest, and when you add them up together, they're basically going to add up to 0. Why? Because this one will go up something like this, right? That's once it reaches this position. And then this one over here is going to come and basically do something like this. And so the crest will add up with the trough, canceling it, giving you nothing. And the same thing happens here, giving you nothing. And so the result of this is called destructive interference because these 2 waves, they add together the same way. But if one of them's inverted, then they come back together and then they can cancel each other out, right? This is happening all the time with light waves in front of your face. It's happening in the water. It's happening in other places as well. Now, these kinds of waves are called longitudinal waves. And it's the kind of wave you get when you take a piece of string and you just give it a jiggle and then it propagates. Now, the next thing we learn typically in physics is about sound waves. Sound waves have a similar math, but the structure of a sound wave is a little bit different than this. So the way a sound wave works is as follows. So let's talk a little bit about sound waves, which is what we study in physics. And you can have constructive and destructive interference of sound waves as well. All right? So if you have, let's say, some sort of pipe, like this. I'll make a little pipe like this. You can have a little end right here and an end right here. And if you have some mechanism of vibrating the air, because that's what a sound wave is, it's vibration of the air. Or if you're underwater, it's vibration of the water. So what happens is you set up a pressure wave. If you can imagine a long pipe, if you had like a piston and you just give it a thump like this, then you're going to very slightly compress the air in front, and then it's going to bounce. It's going to want to come apart from, the high pressure region is going to want to expand, and that disturbance is going to travel down. Think of a coiled spring or a slinky. Give it a jiggle on one end, not up and down, a compression situation. Then the compression wave will travel through it. So this is called a compression wave. Now what you basically have, if you set these things up over and over and over again, is you have these regions of very high pressure right here, followed by regions of low pressure. So these little areas with the dots are the high pressure regions, and the regions in between are the low pressure regions. So this right here is high pressure, right? And the regions that are in between, like this one right here, this is low pressure. Now these are not just sitting here, they're traveling. But if you put a cap on the end, then you can get what we call a standing wave inside, and so you can have musical instruments. You don't have to have a cap on the end. You can have an open end as well, and we can create musical sounds from these compression waves that are inside of these tubes, which are a lot of band instruments. Of course, the waves on a violin or a guitar look more like these compression waves. You can see them going up and down, but the waves that are set up inside of a clarinet or something like that are more of these compression waves, and they have to do with compressing the air inside the tube. Now you can have constructive and destructive interference of compression waves as well. If you can imagine, what if you had a situation where I had one wave coming this way and one wave coming this way, and they add up together in such a way that the high pressure regions are right on top of each other, then they're going to get bigger, just like it did here. But if I have a situation where I have two sound waves coming together and the high pressure and the low pressure regions are lining up, then they can add to zero, just like we did right here. In other words, if I had a sound wave coming this way and a sound wave coming this way, but I had it lined up where the high pressure of one of the waves corresponded or lined up with the low pressure colliding with it, then they would basically they would average out and they would add to zero. And so you can have noise canceling. So you might have seen the noise canceling headsets or noise canceling room. What's going on there is you have a computer listening to all the sound, and it's broadcasting a wave, a pressure wave, a sound wave, which is constructed to add up to the incoming wave in such a way that they add to zero. And so you have a reduction of the noise, or you're trying to reduce the noise in the situation. Now that we've talked about sound waves, in physics we usually talk about a few things related to sound waves, such as Doppler shift. All of these waves have some kind of wavelength. The wavelength is the distance when the wave starts to repeat. So the distance between here and here, for instance, right? Or the wavelength for this wave here, the distance when they start to repeat, like from here to here. It's going up and it's about to repeat again. That is a wavelength. Now, if you put a horn on the front of a train and it's going down the track and you're standing next to the train, you're going to hear it like that, because when we hear the wave approaching, as the train is kind of approaching us, what you have in the situation when the train is approaching you and it's going this way is the pressure waves are building up in front of the train, and it sounds higher pitched because the train is ramming itself into the sound that it's emitting, and so it appears to have a higher frequency, which we hear as, but when it passes, as we hear, why is that? Because this is, if I'm standing, of course, right here. But if I'm standing, right here, and the train has now passed me, the same thing is happening. So except in reverse, the sound waves appear to be farther apart. Why? Because the source is distancing itself before the next high pressure wave comes out. It's going a little farther away, and so it appears that these high pressure regions are farther apart, whereas on the way when they were coming to me, they appear to be compressed together. When it passes me by, then because the source is moving, it appears to space them out, and we hear that as a lower frequency. So when the train comes towards us, we hear high frequency, and when the train passes us by, we hear low frequency. So we hear high frequency, and then it changes lower frequency. That's called a Doppler shift, and we will talk about how to calculate the Doppler shift. Now, it turns out that Doppler shift actually happens with light waves too. And astronomers use it to figure out the distance to galaxies and the distance to stars. But with light, it's not the sound that we hear, it's the color of the light, which is the frequency of the light that changes when things are moving. So when objects are moving relative to us, any waves that come out are going to look a little different than if we were just stationary. All right, so the next thing we learn, taking a big picture in physics, we talk about motion, we talk about energy, we talk a little bit about work and kinetic energy and potential energy and things like this. Then we talk about waves, and there's different flavors of waves. We have the waves on a string, which are longitudinal waves, and we have the waves in a pipe or sound waves, which are compression waves, right? The next thing we learn about typically is called thermodynamics. That's a big word, but it just basically means the study of heat, essentially. So we study thermodynamics. All right, if you remember before, we actually drew a picture of it before. What is heat anyway? A long time ago, in a galaxy far, far away, before we knew much about how the world really worked, people knew that things could be hot and things would be cold, and they knew that things typically tend to cool off. If you take something hot off a stove, it's going to spontaneously cool down. And it was a thought a long time ago that heat, the amount of heat something had, was basically like a substance, almost like an object, like a fluid that could be transferred from one thing to another. Heat was a property of things, and we thought that it was just literally like a cup of water you can pour from one cup to the next. You could pour the heat out of one thing, and it could go into another thing, and that's why things cool off. But it took a long time, many hundreds of years, for people to realize that heat is not a separate thing. Heat is just the motion of the tiny little atoms that everything is made of. Because remember, when we started studying heat, we didn't even know atoms were a thing. We didn't even know atoms existed. But once atoms started existing, we started calculating the kinetic energy of motion of atoms. We were able to prove that the temperature of an object, the amount of heat transferred, is all related to the kinetic energy. So when something is hot, we have a situation, we have a container with gas particles inside, and these things are all moving in random directions, and they're colliding. Remember, we studied collisions in physics. That's where it comes in useful or handy, because when these gas molecules are colliding, they're bouncing off and they're hitting the walls and they're exerting pressure on the walls. So the pressure of an object, the pressure of a gas, is related to how fast the atoms or molecules inside are moving, which is all related to the temperature. So basically, the temperature of an object is an indirect measure of how much internal energy exists of the motion of the atoms inside the thing. But you see, before we knew about atoms, we thought heat was a totally separate thing, but now we know that it's really just kinetic energy. And you start seeing how physics, we think there's so many different things in physics, but actually there's really not that many different things. It's just different ways of looking. Like, water, liquid water and solid ice, they look different, but they're actually the same molecule, H2O, right? And it took a while for us to realize that liquid water and solid ice were actually the same thing. One of them is just colder than the other, and we know now why all this happens. But it appears that they're totally different. Originally, heat we thought was totally different. Now we know it's just kinetic energy of molecules inside. All right? So then we start trying to figure out how to harness the energy of the gas that here. What happens if I heat this thing up? Well, the molecules will start moving faster and exerting more pressure onto the inside. What if I connect this canister that I've drawn on the board to a piston that can move inside of a cylinder? Well, then I can convert that heat into work. Remember, work is when I move something, I do something useful, a transfer of energy that changes the position of something, like maybe the position of a car, or the position of an aircraft, or the position of a satellite, or whatever. I'm doing some work by changing the energy inside of the thing, which is the heat, the internal heat, into some useful work. That whole idea is what we call, it was on the other board, thermodynamics, the study of the transfer of heat, or to make or turn heat into work, basically. So we have a whole branch of physics and engineering that's all studying how we can turn heat into work, right? How can we turn the heat that comes from burning a fuel into useful work, pushing a train? And what kind of efficiency can we get? How much of the energy can we transfer? Is there a limit to that? All of these things. So we can take heat and turn it into work, but we can also do the reverse. We can take some work from the electrical outlet and we can pump the heat out of something, and that's called a refrigerator. So the idea of a refrigerator is actually an engine when you run the engine backwards. In an engine, you try to take the heat from like an explosion or something or burning and turn it into work. But if you have instead some sort of pump or compressor, you go backwards and pump work and do work on the system, then you can pump the heat out. So instead of heat making the work happen, you can do some work from some electric motor, and you can pump the heat out of a box, and that's called a refrigerator. We're going to study engines and refrigerators in detail. Then, after we learn about the laws of thermodynamics, what are the rules in which we can transfer heat into work and so on? There has to be some rules. What are they? Those are the laws of thermodynamics. Then we study something called entropy. Now, a lot of people have heard the word entropy. I'm going to draw something on the board that's a good, useful tool, but just know that entropy goes way beyond the picture I'm going to draw on the board. We study and use entropy in chemistry for talking about when chemical reactions will happen. We study entropy, of course, in physics. We actually study entropy in black holes. We study entropy in information theory, transmitting information, bits and bytes, through the air and over wires. There's actually a calculation for entropy of information also. Entropy is way broader than what I'm presenting here, but in the context of physics, we have a situation as follows. What if I have a container that looks something like this, and what I have is a vessel, and they're connected by a very small vessel, like this. And then what I'm going to do is I'm going to put a stopper in that's going to basically wall off the two sides here. And I'm going to pump this side up with some gas at some pressure. So I'm just going to basically put atoms in here, and it's going to be a known pressure or whatever over here. Now, every one of these atoms or molecules, they're moving, they're colliding with the walls, they're colliding with each other. That's what we have anytime we have a situation with a gas. Now, let me ask you a question. If I draw this again, and if I decide to then remove this thing, I just go and I pull it out, what's going to happen? Now, you know intuitively what's going to happen. What's going to happen is all of these atoms that are all on one side, they're going to spontaneously, through the collisions, transfer themselves to be evenly distributed throughout the entire vessel. So what you're going to have is you're going to have some in the middle, some on the left side, some on the right side. And notice what I did. I had a very high concentration over here. Here I have a lower concentration because everything's spread out, but I didn't count the dots, but let's say it's the same number of dots. It's evenly distributed. Now, what we have said is that basically over here, when all of the atoms existed in one side, everything was confined to one location. We said that there were less states. When I say a state, when I'm talking about a state of the system, I'm talking about all the positions and the velocities of the molecules. Where can they be? Well, compared to this thing, there's less of them because the things can only exist over here. That's less states immediately because the gas can't even live over here. So if a state of the gas is the positions and the velocities, here I have half of the volume, then there has to be less states for the gas. But whenever I allow the gas to flow and do its thing and spread out, we say over here we have more states. Why? Why more states? Because again, the state of a system is how many different possible combinations are there of where the gas could be and all of their velocities, how they are pointing, right? But here, the gas is allowed to fill a much larger volume, so there has to be more states because the gas can spread out to more locations. So we say more states are over here. We can also say that there's more disorder. Over here, we can say there's less disorder. There's less disorder because I know where the gas is more than I do over here. Here, I don't know if this gas molecule, like if I just follow one of these molecules, it could be here, 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 here. It could be anywhere in here. But over here, if I follow one of the gas molecules, it pretty much has to be over here. So there are less states available, and there are more states available, more disordered state over here, right? So what we say is that this is a low entropy state. And this is a high entropy state. And what we basically say is that entropy spontaneously tends to disorder. So the universe that we live in goes that way. The universe that we live in goes from, in general, low energy states or low entropy states to high entropy states in general. And the example of this is this. I mean, I didn't make those gas molecules flow into the other side. I didn't do it myself. The universe did it itself. Why? Because collisions. Collisions randomize the positions of everything, and that is the mechanism that's making it happen. But pretty much every system we look at, if we zoom out and look at it, it's always going to a higher entropy state, a higher, more disordered organizational state. Let's look at a cup of coffee. And a cup of coffee is black. And then I take a dropper and I put a drop of milk right in the center of the black coffee. That's a low entropy situation for the milk because it's only can be in one little drop in the center. But if I wait 5 minutes, the drop is going to spread out and make the coffee uniformly cream color. So originally it's black, then it's black with a dot in the middle or in the top. And then after 5 minutes, if you wait long enough, the whole cup of coffee will turn cream color. The more disorder has happened. Why? Because I don't know where all those atoms are of the milk. I mean, originally they were right on the top in the drop, in the center of this coffee, right? But then after a period of time, they are randomly, through collisions, spreading out throughout the entire volume of the coffee cup. There's more states, more possible locations of where the milk could be if I wait a while. The coffee cup system has gone from low entropy to higher entropy. It spontaneously does this, and generally it does this through collisions. Collisions are causing things to bounce off and randomize their positions, and the universe always in general wants to go to higher entropy. Right? Another example would be if I take an egg and I crack it and I put it in a pan and I cook it. I scramble it. Right? So when the egg was in my hand, it was in a lower entropy state because it was right here. I knew where the atoms of the egg were. And they were right here, and they were ordered. And, well, they weren't totally ordered, but they were more ordered because they were in my hand. When I scramble them, the disorder is greatly increased because I don't know where all the atoms are anymore. I've mixed them all around. The protein structure of the egg is changed. I've added heat. Everything is curled around and kind of like turns into nice scrambled eggs, right? And so entropy goes from this lower state to the higher state, the more disordered state of the scrambled egg, right? Now ask yourself a question. Have you ever seen a pan of scrambled eggs spontaneously reverse itself into an egg? Never. Have you ever seen a cup of coffee that you put a drop of milk in it, which was all cream color, spontaneously reassemble itself into a drop right in the tippy top? No, you haven't seen that. Have you ever seen a situation where a container like this with gas in both partitions spontaneously forces itself so that only half the container contains the atoms and this side contains nothing? No, you've never seen that. We'll talk about ice. Have you ever seen ice just spontaneously form out of water? If we think about ice, if we have a cup of water and we put ice into it, the ice melts and it integrates itself with the cup of water. But have you ever seen a cup of water spontaneously form an ice cube? No, you haven't. Now, for every one of those examples, you might look at me and say, you're crazy. That's just not possible, you know? But the reason that you think it's not possible is because for your whole life, you've never seen it. And you've never seen anything go backwards like that. Because in your mind, you've internalized that our universe only goes one way, toward higher entropy for everything. All right? Now, sometimes when you zoom in on a system, it might go up in entropy or down in entropy, depending on where you're zooming in on. But if you zoom out to the entire Earth or to the entire universe, the entropy is always increasing. And you never see something force itself to the other side of a partition like this, but theoretically it could do that. The collisions that happen over here could just accidentally force these gas molecules in here for a nanosecond. It's very unlikely, but it could happen. The milk in the coffee cup could, through collisions, just randomly collide themselves so that you have a drop of milk right on the top. Yes, it could happen. It is a non-zero chance it could happen, but the odds of it are so low that we never see it. We could have scrambled eggs reassemble themselves into the egg or the ice cube form. We could, through collisions, see that happen, but we don't see it because the odds of that happening are extremely low. So here, when we start talking about entropy, you start getting into probabilities a little bit. Probabilities are fundamental when we get into higher level physics. And this idea of entropy, it slides right into quantum mechanics quite a bit because quantum mechanics is a wave theory. I told you that. It's also a probability theory. So when you combine waves and probabilities, you get what we call quantum mechanics, which we study much, much later. So now we need to turn the page to my absolute favorite topic in physics, and that is Electric fields, magnetic fields, and the famous Maxwell's equations, which in my opinion, as I've said before, are some of the most beautiful sets of equations we have. So what I'm going to do is describe an electric field for you, draw a picture, describe a magnetic field for you, draw a picture, then I'm going to show you kind of what they're doing, then I'm going to write down Maxwell's equations. And if you haven't seen them before, they're going to look scary. But don't worry about it. Don't stress about it. People spend their whole life studying Maxwell's equations. I mean, literally, people study this for their whole life. So if you glance at it and don't immediately get it, don't beat yourself up. We're all like this. But I'm going to explain what the equations mean and what they do. And from that, you're going to have an intuitive understanding as to how light waves happen. All right? Which is not obvious at first, but it will be obvious by the time we're done. So we have to talk about the concept of an electric field. So I'm going to surprise you here and tell you that, remember we were talking about vectors earlier. And we said velocity is a vector because it has a magnitude and a direction. And acceleration is a vector. And force is a vector. And I also said that electric fields were a vector and magnetic fields are a vector. Well, it turns out that in between me and you, or in between me and the camera, there's an invisible field. We call it an electric field. And because at every point in space, there's this thing called an electric field, and an electric field is an arrow with a direction and a size. It's a vector field. So we're not just talking about single vectors, we're talking about a whole sea of vectors. Like if you could put glasses on and just see in front of you the electric field, you would see arrows everywhere. At every point here, there'd be an electric field pointed this way, let's say. Here, electric field pointed this way. Here, electric field pointed down. Here, electric field pointed up. And then there would also be, separately, a magnetic vector field everywhere between me and you. If you put your magnetic field glasses on, you would see magnetic fields, little arrows everywhere between me and you at every single point in space. Magnetic field pointed this way. Over here, magnetic field pointed this way. Over here, magnetic field pointed this way. So these electric fields is what we call there's a whole class of things called field theories, and they exist everywhere in space. And the fields we calculate the fields based on Maxwell's equations, and we actually calculate how the fields push around the particles also using Maxwell's equations. All right, so let me crawl before we walk. Let's talk about what an electric field is. So here we have an electric field. All right, electric field. So here we have a proton. It's just a single particle with a little plus sign. And spontaneously from this proton, we have something called an electric field. It is an arrow which points here. This is the E field, so E with a little vector on top. The electric field exists everywhere, and it's radially directed away from the proton. Now, protons have electric fields that go away. If this were an electric field, if this were an electron here, the electric field would point toward it, but they would still be radially everywhere. So electric fields emanate from any charged particle we know of, protons and electrons, and they either point away or they point towards. They don't curve and do weird things like this. They're either away or towards these particles. So these particles, protons and electrons, everything that matter is made of, they generate around them something we call an electric field. And if I were to take another separate electron and put it here, this electric field that's existing here would push the new particle that I put in, it would push around the particle I placed in the field. So it's a twofold process. Number one, any charged particle produces its own electric field. And number two, any charged particle that you put in the field is pushed around by the field. So this particle makes this field. If I stick an electron here, then it's going to be pushed around by the electric field that is there. Remember I told you electric forces are incredibly strong, much stronger than gravity, millions of times stronger than gravity. So when chemistry comes into play, it's all about how the electrons move and what's going on. So the electric force dominates all of chemistry. That's why chemistry happens, because of the electrons that surround the atoms and electrons that are transferred from one atom to another. So here it's pretty easy to understand. Charged particles make electric fields. They radially go around it. So you might say, how then are magnetic fields produced? So there is no particle that just produces a magnetic field that we know of, okay? But we can produce magnetic fields. They're produced when we take charged particles like this one and we move them like in a current in an electric circuit. Electric circuits generate magnetic fields. Any kind of charged particle like a proton or electron or any ion of an atom, anytime it moves, it generates its own magnetic field. So what does that look like? Let's say I have a wire, and in this wire, I'm going to move these charged particles. Now, in reality, when we build circuits, electrons are the things that are moving. But in physics, we talk about protons moving. We talk about positive current because negative current with electrons gets confusing because everything's backwards with the sign. So when I say electric current moves up, I'm talking about positive charges moving up. But don't get so worried about it. If I talk about positive charges moving up, that's exactly the same thing as if the electrons, which are opposite in sign, move the other way. So don't stress out about the signs. When we study this stuff in detail, we will get to the nitty-gritty of the signs, okay? So what we have here, if we have some kind of current going up through this wire I, then it generates a magnetic field. And the magnetic field forms as circles around the wire. And what I mean by circles is something like this. It's like this. And it has a little arrow like this. And it's like this. I'll just go ahead and draw them all. Whoops, I think I messed that one up a little bit. I'm trying to do, yeah, something like this, something like this, something like this, something like this. So something like this. And like this. All right, first thing to notice is that the fields look totally different. Because the electric field are lines that come out of particles, but the magnetic field form these circles like this. So we call this the magnetic field. And the symbol that we use for the magnetic field is B, with a little vector on top because it's a vector field as well. All right, so far we have two totally different kinds of fields. One of them is called an electric field. It spontaneously happens anytime a charged particle is just sitting and not moving. And it radially comes out away from the particle, right? And then we have another kind of field called a magnetic field that happens when particles move, charged particles move, like electrons or protons. In this case, it's like positive charges moving. And the field forms these rings. So the structure of the field looks different than this, but it's still a field that forms around charged particles, but only when they're moving. Magnetic fields only happen when they're moving, right? All right. Now, here's the punchline to this. These are how the fields are created. Electric fields are spontaneously creating out of any electron or proton sitting there, and magnetic fields are created anytime they're moving. Right. Now, once the fields are there, then any charged particles like electrons or protons you put inside of the fields, they start to get pushed around by electric and magnetic forces. So if I take an electron and put it here, it's going to start to move. If I put a particle here in the magnetic field, it also experiences a magnetic force when it's in motion. I guess it should say it's a little different. If the particle is in motion in this field, it'll experience a magnetic force, right? But the point of it is that charged particles can have a force acting on them when they're placed inside of an electric field and when they're moving inside of a magnetic field. But once they start moving, they start generating their own magnetic fields, and they have an electric field also present with them. So if I take a particle and I put it here, it's going to start moving. If I take a particle and move it inside of here, it's going to have a force and start to be pushed in a certain direction, but because it's moving, it's generating its own magnetic field. So you see kind of the feedback that's kind of like happening here. You have a field that exists, you put a particle in there, and depending on how it's moving, it's going to experience magnetic or electric forces that are going to push it. But once it starts moving, it's going to generate its own fields, which are different from the ones to begin with. So there's this crazy imbalance going on and feedback that's happening all the time because the fields that exist are pushing particles, but once the particles start moving, they're generating their own fields, which are electric and magnetic fields also. So now we need to quantify this because people did experiments for hundreds of years on how electric forces and magnetic forces worked. What happens? How much of a force happens? How much of a magnetic force happens? How much of an electric force happens? When do you get a force? When do you not get a force? And eventually, Maxwell wrote down his 4 famous equations that describe how these electric and magnetic fields interact with each other and also how they interact with charged particles that are put inside of the fields. So let's write down Maxwell's equations. These equations are extremely important. They're still used today. These are not like out of date. They're used for everything from antenna design to figuring out how things are going to propagate through space. Radio waves propagate through space. Einstein used the Maxwell's equations to formulate general and special relativity theory. So that was like a starting point for Einstein to move on and develop relativity. I mean, they're incredibly useful. They're something that probably are always going to be useful and probably never really go out of date, okay? And they were developed a long time ago. I'm going to write these equations down, and I want you to keep two things in your mind when I write them down. Number one, there are different ways to write these equations. I'm going to write them down in the way I want to write them because I think it's easier to talk about. But I can write them down in a different form I'll talk about in a minute. You might see in your textbook a slightly different way of writing them down. But they're the same set of equations. They just might look a little different. The second thing is, the first time you look at them, you're going to be like, I have no idea what this guy's talking about. I've never seen mathematical symbols like this. Take a deep breath. My point here is to give you a 100,000-foot overview. And remember, when I said people study this stuff their whole life, I really did mean it. People study it for their they get their PhD, and then they go study it for their whole life, trying to develop whatever it is they're trying to develop. So here are the famous Maxwell's equations. Here's the first one. You have this upside down triangle, not a right side up, an upside down triangle. That's called a del operator, dotted with the electric field, and that gives you rho over epsilon 0. You're like, whoa, I have no idea what this is. Just calm down for a second. I'm going to explain what these things mean. We're not going to do the full glory of the math, but I'm going to explain intuitively what they mean so that when we get to that later, you'll understand, oh, I remember he told me that this is what this sort of means. And then we'll dig into the details later. This is the first equation. It's actually one of the smaller equations. The next equation is upside down triangle dotted with the magnetic field gives us 0. The third equation is upside down triangle crossed. This is not multiplication like in 4th grade. This is the cross of two vectors of the electric field. And that's equal to negative of the partial derivative of the magnetic field with time. This is not a regular derivative. This is called a partial derivative, and that's because the magnetic field, it can change in space and in time. So this is the change in the magnetic field with respect to time only. And then here's the last equation. Upside down triangle crossed with the magnetic field, called the curl of the magnetic field, is equal to mu naught J, that's a vector quantity, and then plus mu naught epsilon naught. You're like, whoa, what's all this stuff? And then partial E with respect to T. All right, these are the Maxwell's equations. Just soak them up, absorb them. No, I don't expect you to know anything about what they mean. Of course not, nobody would. Because they're just gobbledygook symbols. But let's go through them. Because, you know, I've taken, I'm not even sure how many, 4 or 5 or 6 electromagnetics classes over the years. And believe me, even when you get to the end of it, there's still stuff that you don't really realize, and you're still learning about them. So, you know, I know a few things about these equations, but I certainly don't know everything there is to know. And neither will you. And that's okay. We can always learn together, right? I can learn by talking about it. You can learn by listening. And then you can learn things that I never knew and vice versa. That's the way it works, all right? So this upside down triangle comes from calculus. You usually get to it in calculus 3. And this is basically a vector derivative that's happening in all 3 directions, x, y, and z. Because you got to remember, these electric fields, notice you have electric field here, and you have magnetic fields that are popping up here. Electric fields here. So these equations are all relating how the electric fields and the magnetic fields relate to each other. That's what it basically boils down to. Because it turns out that when you cause a change in the magnetic field, it causes an electric field to happen or to occur. But when the electric field changes, it causes the magnetic field to occur. But when the magnetic field changes, it causes the electric field to occur. But when the magnetic field changes, I'm probably misspeaking, but you get the idea. A change in one field causes the other one to happen, but when the other one changes, it causes the other one to happen. So it's like this yin and yang, and this is what leads to waves. Because a wave is a combination of an electric field and a magnetic field that are changing together. Because when one of them changes, it causes the other one to happen, but as soon as the other one changes, it causes the other one to happen. And so they propagate through space as a nice pair called an electromagnetic wave. And I'm not going to do it here, but when you study this stuff in detail, you can combine these equations together into what we call the wave equation, which tells how light waves propagate. So light waves come out of this. Light is or at least in the wave theory aspect of it, it's a wave, which is a propagation of electric fields and magnetic fields. Because I told you, electric fields are everywhere. Magnetic fields are everywhere. And it turns out that a disturbance in the electric field can propagate coupled with a disturbance in the magnetic field and propagate through space as a wave. But it takes both of them, electric and magnetic fields together, to make the wave propagate. All right? So what do these equations mean? I think I'm going to take this off because I want to write some notes down on the right-hand side. This operator is taking the derivative of the electric field, because upside down triangle means derivative, but remember, it's not just a derivative, it's x derivative, y derivative, and the z derivative, and it's dotted with, because we're going to get to vectors later, this is a vector operator dotted with a vector field. So what you're doing is you're multiplying, you're taking a derivative in all three directions, essentially, and you're adding them up. Let me say that again. You're taking the derivative of this thing in all three directions and you're adding them up. So when you look at div, this is called the div operator of the electric field. It's the outward flow of the electric field. So it's the outward, this thing right here is the outward flow of the electric field. That's what this does. You're taking the derivative in the x direction, the derivative in the y direction, the derivative in the z direction, how they're changing in those directions, and you're adding them all up. And this is what's called the div operator of the electric field. It's the outward flow. How much outward flow of electric field do you have? And this outward flow of the electric field that you have, it's equal to the charge. This row here, this is the charge density. So this is the charge density, or basically the charge that you have there. And this is a constant of nature. Epsilon naught and this one down here, mu naught, that's the permittivity and the permeability of space. Those are just constants of the universe, so don't worry about them right now. But basically, what you're saying is the outward flow of the electric field, if you could sum it all up in all directions, is basically equal to or proportional to the charge density of electrons or protons or whatever it is. So what it's saying is the electric field is basically generated by charges. So I'll write that down. The electric field is caused by charges. Because the outward flow, the sum total of the electric field in all directions is equal, there's a constant here, so forget about that, equal to the charges that are inside. And look at what we drew. We said the electric field is basically generated by this proton here. And if there were an electron there, it would be going the other way, but the electric field would be generated by the electron. The outward flow meaning how much net flow out, you can think of these arrows as kind of flowing out. How much outward flow do you have? If you sum it all together, then it's basically equal to the charges that are on the inside. So this first Maxwell's equation, it basically says that electric fields come about because of charges, which is what I drew on the board. Mathematically, it's saying that the outward flow of the electric field is equal to whatever charges are on the inside. All right? Now, when you study this in physics, and we will, you see these equations often written in terms of integrals, where we add up the electric field and we set it equal to what's on the inside. But I like writing it like this for reasons that are going to come later, and you don't see it very often in a lower level class, so I want to enrich you a little bit, right? Okay, let's talk about the second equation. So if this is the outward flow of the electric field, then this one right here has got to be the outward flow of the magnetic field. All right, and it's saying that the outward flow of the magnetic field is 0. It means that there are no particles that generate a magnetic field that radially go away from it like that. Notice I said the electric field did that, but the magnetic field was forming these closed loops. So if I draw a box or a circle and try to add up the outward flow out of some spherical region, what am I going to get? I'm going to get 0, because all the magnetic fields form closed loops. They form closed loops. There is no magnetic particle. You see, electrons and protons generate electric fields that go away radially. That's why the divergence of the outward flow of the electric field is equal to a number, but the divergence of the outward flow of a magnetic field is 0, because magnetic fields always form closed loops. So there is no outward flow. If you draw a boundary around any region of space, like if I drew a boundary here, there would be equal number of magnetic field lines going in and equal number coming out. So the total number, the outward flow, would be 0. So what the second equation really is saying, right, is that magnetic fields form closed loops. That's it. That's what it means. That magnetic fields form closed loops. Now, people are still, these equations look very similar, but of course the zero is different than this. People are looking for magnetic particles. Like modern physics, they're looking for magnetic particles. We haven't found any yet. So this is where we think is true. All right, now let's go to the other two equations. So that's what these two equations mean. What do these two equations mean? All right, there's a new operator here. Upside down triangle. This is not multiplication like in third grade. This is the vector cross product. So this is the dot product. This is the cross product. We learn about those in physics and calculus. This is called the curl of an electric field, and it measures the rotation of an electric field. You see, everything here is going outward, right? But a rotation of an electric field might literally be, or any kind of field that's rotating would be, what if you had something going on like this, where the vector field was doing like this? You see how there's kind of a rotation going on here? Because it's not like everything is going radially out. There is some sort of rotational, kind of right-hand rotational thing going on here. And this curl, these derivatives, remember these are derivatives in x and y and z, when you operate on it using a cross product of the electric field, this is telling you the curl, or how much of the electric field is curling. That's what it's basically telling you. The curl of the electric field is equal to negative, forget about the negative, how the magnetic field is changing. What it's basically telling you is an electric field is generated if the magnetic field changes with time. That's the key cutaway. How the electric field is generated is it's a rotational thing. The curl of the electric field is equal to, the rotational amount of the electric field is equal to how much the magnetic field is changing with time. So remember what I told you. Changing electric fields cause magnetic fields, and changing magnetic fields cause electric fields. This is how it happens. Because if I have a magnetic field that's changing in time, then there must be some electric field associated with it. That's what this is saying. So this means that this equation right here means that electric field is caused by changing magnetic field. Literally in words, this is what it means. Electric fields are caused by a changing magnetic field. And what do you think this is going to be down here? Now let me cover this up. Let me cover this term up here. This one is saying is that magnetic fields are caused by a changing electric field. Forget about the constants. They're just constants of nature. So basically cover up all of this right here. What it's saying is that magnetic fields are caused by changing electric fields, right? Which is what I told you would happen a second ago. But they're also caused by this thing. This J is the electric current. So a curling magnetic field is caused by two different things. Can be caused by two different things. They can be caused by electric currents that are just flowing. Then you would have a curling magnetic field. Remember, a curling magnetic field literally has some kind of rotational thing. It can be caused by an electric current, J. We call it J because it's not just a current, it's the current density. Current per area, per cross-sectional area. It doesn't matter. It's the electric current. And notice what I drew here. Electric current, magnetic field forms these closed loops right here. And so the curl of a magnetic field, the magnetic field is generated by electric currents that flow, and they're also generated by electric fields that are changing. That's what it's saying. So the last equation says that B caused by one of two things: current, flow, and changing electric field. All right, so do I expect you to become an expert in Maxwell's equations? No. Nobody is, actually. But I don't expect you in 20 minutes or whatever to absorb these equations and just understand them, because it really, when you blow them out, the math gets quite complex. It's very complex because there are 4 equations. They're all interrelated, and they're all related to vector fields. But still, you can understand what they're telling you, and that's all I care about you knowing right now, to understand the beauty of what these equations really are. The first one is saying that the outward flow of an electric field is caused by charges that are inside, and that this electric field emanates radially from those charges, just like this. This one says that there is no outward flow of magnetic fields, And that's because magnetic fields form closed loops. And this one basically is indirectly saying that there is no particles that generate, just by themselves, magnetic fields. The particles have to move. You have to have electric currents to make a magnetic fields. Without the other term that was coming to in a minute. But there is no particle that generates magnetic fields by itself. This one is saying that electric fields are generated when the magnetic field changes, and they're generated in a twirling fashion. And this one is saying that magnetic fields are generated by electric fields that are changing. So these two are coupled together. Electric fields are generated when magnetic fields are changing. Magnetic fields are changing when magnetic fields are created when an electric field is changing. So the E field is created when the magnetic field changes. The B field is created when the E field changes. But the B field can also be made by a current flowing through a wire. So these two equations together can be combined later in advanced math to write down what we call the wave equation. And it makes sense that a wave would propagate out of this situation, right? Because it's literally saying you have these two quantities, and one of them is generated when the other one changes. But because this one changes and generated this one from 0, let's say it was at 0, then you start changing this and you make some non-zero field. Well, as soon as you create it, it's changed because it's come from 0, then you make a B field. And then this one is changing, which goes back into here, and they just keep feeding on each other because when one changes, they cause the other one. And then when that one pops up, it's changing and causes the other one. And so they form a wave, which can propagate through space, and the speed of this wave propagation is called the speed of light. The speed of light. All right, we're getting to the end of the road. That's the main thing I wanted you to understand, that these disturbances, they come in pairs. They come in pairs because Maxwell's equations show how they're coupled together, and this is why I write them this way, because it can more easily show how they're cross-coupled and how a wave would come out of it. So, what does a wave like that look like? Probably a good idea for you to know this because, I mean, this is how everything you see works in real life, an electromagnetic wave, right? So if we call this the x direction, then we can basically have a situation where we can have, and I'm probably going to mess this up, I apologize in advance if I do, but you can have an electric field that is like a sine wave that goes up like this, right? And this, I guess I'll just draw the other one first, and hopefully I get it right. I'm probably going to mess this up. This is an electric field that's oscillating like this. As soon as this electric field is changing, or then it's going to create the magnetic field, which exists 90 degrees perpendicular to it, which you can prove using math as well, and it goes something like this. It's going to go something like this. And you got to apologize. This is my attempt at making it look kind of like flat. So here, this field is in the plane, the flat plane like this, like this. Like this. And this one is the magnetic field, right? And then the other field is up and down. 90 degrees. This is a 90-degree angle perpendicular between them. And these are oscillating electric and magnetic fields. So, let's look at Maxwell's equations. What it basically says is that when we have a changing magnetic field, it makes an electric field. We have a changing magnetic field, and it creates a changing magnetic field, creates a changing electric field, right? But then when this electric field is changing, it causes a change in the other field. And so they go together through space like this. All right, so, and the idea that it's a curl, this is what, it's very hard to describe without actually getting into the math, but this curl operator, when you blow it out and you combine it with this equation, it predicts the wave propagating in the E field and in the B field are in 90 degrees to each other, and they propagate through space. So changing magnetic field creates electric field, but once this electric field changes here, it creates a magnetic field, and then the process just continues, and so they just kind of swim through space. Now I'm doing my hands like this, but really one of them's going up and down like this, and the other one's going side to side like this, and they're 90-degree angles to each other, but they're propagating perpendicular to each of them. So if the electric field, if one of the fields was up and one of the fields was perpendicular, then the direction of propagation is to you, toward the camera like that. And the speed of this propagation, speed of light. Now you don't see the speed of light here in these equations, but you can, when you combine them together and you calculate the speed of the wave, the speed of light is the speed of the wave that comes out of that. Now after we talk about electromagnetism, and electric fields and magnetic fields in physics, we talk about electric circuits. How do you harness this to create a circuit to do something? We talk about optics, when things flow through, light goes through lenses and they can be bent. We talk about refraction, things can be bent going through another material, and diffraction, when they can be bent going around a corner, for instance. And then I'm leaving the best for last. We cannot cover it in this lesson, but we have two gorillas of importance. One of them is called relativity theory, and the other one's called quantum mechanics. And they form their own courses, really. But in general, relativity is all about the idea that time is not a constant. When we wrote down the equations of motion, we had time, t, in there. And it makes it sound like there's just a background tick that's happening all the time in this universe. Tick, 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 all the time. It's very constant. But it turns out that the flow of time depends on your state of motion. It's not a constant. I know that sounds crazy and weird, but there's a mountain of proof that time is not a constant. It changes depending on how you move or on what kind of gravitational field you're in. But the flow of time is not a constant. And then quantum mechanics, that's the other big thing. See, I spent all this time writing down Maxwell's equations and telling you this is how waves propagate and all this stuff. But the reality is that's not really true. Or it's not the full truth, because we know that light doesn't just obey Maxwell's equations. Light is a little more complicated than that because there are some experiments we could not explain using only Maxwell's equations. It turns out that light is consisting of electric fields and magnetic fields, but it only comes in little chunks, little packets. And these little packets of energy are called quanta. That's why it's called quantum mechanics. And so according to wave theory, you could just have a wave as big as you want, as long as you want, and nothing limits it. But in reality, we know light only travels in packets. And we know that matter only also comes in packets called electrons and protons and things. It turns out that light is a wave in packets. And it turns out that matter is also a wave. And I know that sounds even crazier, but our modern theories, which are extremely accurate, say that electrons, protons, atoms, they're all essentially waves, wave packets. And that's the entire subject of quantum mechanics. So that is basically what you study in physics. You start with motion, you go through energy, you go through thermodynamics, you go through waves, you go through electricity and magnetism, and you finally land at relativity and quantum mechanics. And it's thousands of years of learning. It's not something you can learn in a weekend. It's something that you spend your whole life learning. My only goal in this introduction was to get you excited, to try to hopefully inspire you to learn some of the things that people spent their whole life trying to understand. And that maybe one day when I'm gone, some of you will take your knowledge and discover the next best thing, the next big thing. That's really all I want. And I'm hoping that this introduction will give you the fire that you need to slog through some of the work that we're going to have to do together. So follow me through the next several lessons, the next many units, and travel with me on this journey as we take all of these topics, we roll up our sleeves, we dive in, and we really calculate how to use these things, how to understand how they work, and to build up your skills so that when you get into the point where you're doing the next thing in research, engineering or physics or chemistry, that you can discover the next best thing.
Learn anything at mathandscience.com.